Alright, in this problem here we're looking at the reaction between carbon and water to produce CH4. I think this is just because of the scaling when I copied and pasted it got a little wonky. And carbon dioxide. So this is methane, this is natural gas. Most of the stuff that comes out of our gas jets there in the lab is this material here. And then carbon dioxide. So we want to determine the standard enthalpy change, or delta H, for the reaction from these subreactions that we know the delta H prime or delta H naught for. So if we notice here, we've got water kind of everywhere, and just like how oxygen's kind of made our combustion reactions a little difficult to figure out what's going on, water is going to do the same for this. So water is not going to be a really good hint for us to figure out, well, do we flip one of these? Which one do we use? How do we try to get up with two? And there's three down here. So we're going to hold off on the waters. But if you notice here, we only have carbon here, and we only have carbon there by itself. So this is a good indicator. We'll start with this first equation. And carbon's a reactant, and it's a reactant down here. We want to have two carbons up here. We only have one here, so we're going to have to double this reaction right now. So we're going to take two carbons and water to produce carbon monoxide gas plus hydrogen gas, and whoops, forgot to double everything, so let me double that, and double that. And so our delta H naught is going to be 2 times positive 131.3 kilojoules. We don't have to switch the sign because we didn't have to flip this equation. Alright, so that takes care of the first equation. Let's take a look at our second equation, see if this is a good place to go. Here we got carbon monoxide in both of these, so carbon monoxide is not up here. We've got carbon dioxide being produced in here. We got carbon dioxide being produced in here. So this equation here looks like it's set in terms of it's in the right direction. We have one carbon dioxide up here. We've got one carbon dioxide here. So we're just going to leave this one as is. So we've got carbon monoxide gas plus water as a gas, or steam, I guess, produces carbon dioxide plus hydrogen. And our delta H naught for this one is going to stay our negative 41.2 kilojoules that we had up here. And then finally, let's take a look at this last equation. How can we set this up? Well, here's methane, CH4, carbon tetrahydride. And here's methane, carbon tetrahydride here. Same coefficients, 1 and 1. However, here we've got it as a reactant. Up here, we have it as a product. So we're going to have to switch this. We're going to have to flip it around. So we've got 3 hydrogen gases plus carbon monoxide is going to form methane, CH4, plus, that's gas, plus water, and that's a gas. And our delta H is going to be 206.1 kilojoules. Alright, so let's figure out what's going to cancel out. So I've got a carbon here, no more carbons anywhere else by themselves, so that's going to stay. We're going to keep that. I have 2 waters over here, and I've got 1 water down here. But actually, I've got 1 water here too. So let's cancel that water and that water. We don't have to worry about changing coefficients up here. We're producing 2 carbon dioxides up here, and we should have another, 2 carbon monoxides up here. We don't want to have any carbon monoxides whatsoever, so that carbon monoxide, that carbon monoxide, and that carbon monoxide are going to cancel. We have 2 on the right, 2 on the left, so they're good. And then let's take a look at our carbon dioxides. We've got a carbon dioxide over here, nowhere else. We have 2 hydrogens up here, but we've got 3 hydrogens. Actually, we have 3 hydrogens here, so they're going to cancel. And we're left with water and carbon to produce carbon dioxide and methane. And if we add these up, we should end up with a delta H of 15.3 kilojoules. That's this problem.